Okay. Right. Um, yeah. So I'm not sure, like any one of you are new. Suppose if you are, so first, if this is your first class, go through the previous classes, right? So where we discussed. So that is just an architecture. So we all know the architecture of the SQL Server, right? So we had a discussion how select query works and how update query works. And I'm not going to go through again. So please go through the previous recording, uh, two sessions, right? So we'll go forward from here, right? Um, So in a high level, let's say, for example, this is your query, right? So you are executing a query and that will go for parsing, right? So parsing as in where it checks that syntactical errors and then it will go for query binding. For example, if the syntax is correct, then it will check the schema binding. For example, let's say you have a table. The table uh, for example, ABC is a table, right? If you execute ABC, select star from ABC and select star from uh, test.abc. These two are different because second one is so executing under test schema. The first query executes under DBO schema, right? For that reason, it has to identify which schema we are executing, right? So that is what it is, schema binding. It is required. So algebraizing, so we call it as. Then once that is done, then it go for optimization. Optimization where we see different phases, right? Whether it is a simplification. If it is a simple query, select star from table. If it is a simple query, it is considered as a pre-optimization or trivial execution, and it terminates, it generates a plan and it will not go for full optimization, right? So that is what it is. And second one is whether the statistics are updated, and then based on that, like, so it consider that statistics and do a so internal loop to identify an optimal plan for the query, right? So it checks that multiple, combinations, right? To see what is the optimal plan for your execution. It will not keep checking for the good plan. It will get whatever plan it detects that is an optimal plan for your execution. It stops searching further and generates a plan for our query, right? So see here, the goal of the query optimization is not to find the best plan, to find the good enough execution plan, right? So once the optimization is completed, then it generates a query plan, right? The plan will be stored in the plan cache for the later usage, right? So this query will go for, this plan will be going for query execution, and query executor will takes care of the execution of the query, right? So while executing, it needs some data to read or it has to update. Then it will connect to the database, the storage engine. It connects to the storage engine, right? So to process its operations, because storage engine where we have the data stored, right? In the data cache, right? So storage engine where we have the data, right? Suppose if data cache doesn't have enough pages or so if data to satisfy the query, then the buffer manager will connect to the data file and request for the page to process, right? The page will be pulled by the buffer manager and keep it in the memory. That is your data cache. Once the page is available in the data cache, the operations will be performed, right? So that is the select. If it is in terms of any DML operation, before even so processing that, it will write the transaction data into the transaction log file. That is what we call it as a write ahead logging, right? So the make sure the data is durable, right? So we have something called acid properties durable, D. So that durability is nothing but it makes sure that data is written to the transaction log file, so that whenever there is a crash happens, the logs will be recovered from the transaction log file during the recovery phases, recovery process, right? So it will write into the transaction log file, and parallel it will write into the data cache as well. So frequent checkpoint, it will flushes the pages from the data cache to the store disk. That is your data file. Data file to the data cache, data cache to the data file, it will flush frequent checkpoints, right? So checkpoints will not clear the data cache. It will just copy the pages and keep a duplicate or kind of pages into the data file and removing the dirty bit from the data cache, right? So checkpoint also does one more thing. It will flush whatever logs available in the log cache, right? So log cache is it is inside the memory into the transaction log file, right? So that is what checkpoint does, frequent checkpoints. And whenever there is a crash or recovery starts, the recovery starts from the last checkpoint LSN, right? It identifies the last checkpoint LSN. From there, it will start recovering the data or the transaction, right? So the pages will not be removed from the memory by executing checkpoint, right? There are different types of checkpoints. One is manual checkpoint, automated checkpoint, and indirect checkpoint, and internal checkpoint, right? So automatic checkpoint is executes automatically every one minute or so, like so based on um the I mean automatic checkpoint, it executes. Internal checkpoint, some operations, let's say for example, you take a backup, right? So that requires a checkpoint. You take a snapshot, that requires a checkpoint. If the SQL service is restarted, that requires a checkpoint, right? So those are all some internal background operations will trigger a checkpoint, right? So indirect checkpoint where we have starting from 2012, we have something called um, target recovery time. So the target recovery time, for example, by default, it's set to 60 seconds. That is 1 minute. So what is that? It will make sure the database, whenever the crash happens, the database should be recovered in 1 minute. So how 1 minute is possible is the indirect checkpoint. So internally, it calculates the number of pages. Then based on that pages, that count, let's say, for example, it calculates the number of pages are 10. If number of pages are reached 10, so then checkpoint triggers, right? So frequent checkpoint happens, right? So that it will understand when the database would be able to recover, right? So that is the high level of indirect checkpoints. So we are not going to detail about the indirect checkpoints and all, like, so those are the basics. And we have something called manual checkpoint. For example, if you want to execute query, right, you can just execute um, checkpoint, right? So if you execute checkpoint, so that executes successfully because um, you can execute checkpoint manually, right? So that is how that you will have to do that. And it will not remove the pages from the cache. It will just copy the pages. How the pages will be removed? There is another process called lazy writer. It checks if there is any memory pressure or any memory notification. It responds to the memory notification, either it is an internal or external memory pressure. So we are going to discuss in detail in memory section, like what is the internal memory pressure, what is the external memory pressure in SQL Server, right? So lazy writer will respond to either internal or external memory pressure, and it will check what are the least recently used pages. Let's say you have 100 pages in the data cache. Let's say you 10 pages are currently using, 10 pages used an hour before, and remaining 80 pages are used a while ago, like, so a week or 10 days or even 2, 3 days before, whatever, right? So in this case, it checks what are the least recently used. So these two are considered as a recently used because this is currently using. These 10 used 1 hour before. Whatever 80 pages that we have are not used recently. So we consider this as least recently used, LRU. Then it will be remove those pages from the cache, right? So those pages will be removed from the cache, and it will release the memory, right? So for the other operations, either it is an external memory pressure, so that it will release to the Windows operating system. If it is the internal memory pressure, it will release to internal operation, right? That is how, like, so high level what we discussed about the architecture. This is the query life cycle that we have discussed. Now let's go with further topic. In architecture, if you remember the if you remember this diagram that we discussed, and there are net libraries are fine because network libraries are something which client side and server side you will have the network library where the communication, where the handshake happen between the client and the SQL database. So second piece is the user mode scheduler, right? So user mode scheduler is nothing but SQL operating system, right? So user mode scheduler is nothing but, so how it is scheduling. So we are going to talk, and this section is something that we need to understand, right? So how the scheduling works, right? What is scheduler and how the scheduling works. Let's say, for example, you are executing some query. Let's say select star from table. You are executing this query, right? So we understand as soon as you execute this query, this needs some pages and gets the data, whatever it is, and it communicates and all that we know. So what it happens once it is connected to the SQL or database, right? What happens once it is connected to the SQL server? Who will execute? How this will be executed? And where this query executes, right? So that is what called UMS, user mode scheduler, right? So that is the topic that we are going to discuss and understand how the query process with its execution, right? Mm. So SQL operating system, right? Or user mode scheduler, right? So these are all just a high level of what we need to understand in this session, right? So before executing, let's understand few basic terminologies, right? So a process, a thread, right? What is a process? What is a thread? We call it as. Let's consider that this is your computer. This is your mission, right? So this is your mission. So in this computer, you have different applications, right? So we call it as an application, and SQL Server is one of the application, is one of the software, right? So let's consider that if this is your SQL Server you installed, and this is, you can consider that as a notepad on this computer, right? So this is notepad, also one of the exe executable, one of the application, right, where you have on the computer. So you can consider this as a PowerShell, right? PowerShell also one of the application. And anything, right? So any software that you install on a computer, we call it as an application. Let's say it is your anything, Power BI, right? So these are the softwares that you install on a computer, right? So these are the softwares that you installed on the computer, inside the computer, right? Each software, we call it as a process, right? Each software on the computer, on the server, we call it as individual process, right? So individual process. So SQL Server is a process, PowerShell is a process, Power BI is a process, and Notepad is a process. So these are all called as processes, right? So I have a computer, I installed multiple applications. So each application is called as a process in terms of so in terms of IT world, we call it as a process. Let's consider that, right? So each process, the the operation has to be executed. Let's say, for example, SQL Server, you want to execute some queries, right? So in Notepad, also in backend, that needs to be executed some process, some operation, right? PowerShell also, you will have to execute something. Likewise, Power BI, you connect to the Power BI and you want to get a few reports, right? So all will be considered, I mean, one sec, right? So these are all, we call it as a process, right? So this is one process and PowerShell is another process, and SQL Server is a process, and Power BI is a process. Now, so process itself will not perform anything. For example, take an example, you are working for an organization, right? So let's say, for example, ABC an organization, or in any company that you are working for. ABC is an organization. So if you're working for an ABC organization, then what happens? This organization itself will not work, right? So who is working for the organization are something called employees, right? So who are working for the organization? For example, there is a project. There is a project called. So what is this project? Anything you can consider that is a banking project, or it is a financial project, or any project, doesn't matter. So you have a project allocated for this organization, right? So we got a project. So who work this project? The organization itself will work this project? No, organization is the high level, right? So based on this organization, we got the project. That's fine. But who handles this project is something called employees. So employees, right? Or we call it as a worker, right? In just a terminology. So we call it as a worker. This worker will handle the project to complete. Once the project is completed, it is, so it is marking as completed, right? So here, the same logic, the SQL Server is considered as an organization or a company. So whenever there are queries executing, this process will not execute anything. Our process will not do anything. Who will do that? There are something called workers in the SQL Server process, or we call it as, in a SQL terminology, we call it as a thread, right? Or in Windows terminology, we call it as a worker. Even in general sense, or general terminology, we call it as a worker, which actually handles the work, right? Handles the work. So now, whenever there is an execution, or whenever there is a something executing, SQL Server will not execute on its own. Who is taking care of the work is your thread or the worker. The same thing I was talking, right? The organization, it's a org level, will not do anything. So who is actually working is employees under this organization. The same thing, SQL Server is a process, will not perform anything on its own. So it needs worker or a threads which has to handle the work, right? That's what it is, right? So the process and the threads, right? If you see here, process as an execution unit, right? It is considered as a container, right? The process is a container where you will have multiple processes, multiple tasks will be created, right? So here you see the task one. So you can consider the task one is your select query. Second one is your update, delete, insert, some different tasks that you are creating. Or even it is an internal task. Let's say checkpoint, lazy writer, or some background threads, right? So this task can be anything. And this is thread as a multiple execution context, right? Process as an execution unit. Execution unit is nothing but it is just a container for the task. The process is considered as a container for your operations, and threads are inside this process. See here. So inside this process, who is handling this task? Who is handling this task are your thread. Thread one will take care of one task. Thread two is take care of another task, and thread three, right? So different workers will take care of the task. The same thing that we were talking, right? So in an organization, so multiple projects or a project has to be handled. The project is a larger piece, right? So the project will be divided into multiple segments, multiple pieces, and will be allocated to multiple workers or multiple employees. The same thing, you'll have multiple tasks inside the process, and each task will be handled by different worker or different threads, right? So threads are the smallest executable unit which takes care of the work, right? So if you see here, processor is just a container. Okay, we'll talk about the processor. Let's understand this as a process. Mm. Process does not execute or run. Rather, this process will not execute. Process is nothing but an application. Will not run. Rather, threads associated with the process run on the processor. Right. So I will talk what is this processor. But for now, understand that process is just an application. Will not execute on its own. Who is executing are the threads which takes care of the execution. A process as such contains several individual tasks that may or may not be depending on each other. Yeah. So as I said, it can be a one project or it can be different projects. It may or may not be depending on each other. This makes us to do a design change, whatever. Like so, it doesn't matter. This is just a statement, whatever. Okay. Now, where this executes, right? So we understand it it executed by a thread, it executed by a thread, it executed by a thread, right? For this process, right? Where this will be executed, this will be executed on CPU, right? It executes on the CPU to perform your operation. So it needs some, so you can consider that platform to execute, or it needs some platform to perform some operation. So what is that platform that we are giving is your CPU, the resources that we require to execute this task, right? Where that executes is on the CPU, right? In the SQL terminology or even Windows terminology, we call it as a processor, right? So each CPU, we call it as a processor. For example, since it is a process, right? This process has to be executed on CPU. So we call it as a processor. It has to be processed, right? CPU, we call it as a processor, right? Remember, CPU, we call it as a processor, right? Each CPU, let's take, um, let's say you have 4 CPUs on the computer. One, two, three. We call it as a CPU 1, CPU 2, CPU 3, CPU 4, right? Each CPU is mapped to a processor. I mean, it is actually both are same. So processor, you can consider that as a logical, right? From the SQL world or SQL perspective, we call it as a processor. So it is considered as a logical unit, right? Processor 1, processor 2, processor 3, processor 4. So where SQL works, I mean, SQL executes threads in terms of in the processor. We call it as a processor in SQL terminology, or even Windows terminology, we call it as so the CPU, right? CPU is at kernel level, we call it as, right? So we have a CPU where we have a processor, right? I'll show you just a moment. Um, for example, if I go here, task manager, performance, and if I click on CPU, right, see here, you see that logical processor, right? So you have 4 CPUs or 4 cores mission where you have the 4 logical processor. The processor are mapping one to one. The CPU and processor are mapping one to one. So number of CPUs that we have, it will be mapped. Suppose if I see here some review, sorry, logical process, right? So I have 4 CPUs. I have 4 CPUs, and we consider that as a logical processors are 4, right? In SQL terminology, for example, select star from mm, so okay, so one thing. So these processors are nothing specific to SQL, right? So that is what just wanted to make sure it is not specific to SQL. So where I see that Windows machine, so you have this CPUs, and each CPU is logical mapped to a processor, right? So we have a 4 processors system on this computer, right? So this is nothing specific to SQL. For now, understand, processor is nothing but a CPU that we have on the computer. Now, so where this threads executes on the processor, right? So okay, so this is a high level of the thread. A thread is a unit of execution within the process that we already discussed. Multiple threads can exist within a process that we discussed, right? Each is given a small amount of processor time, right? It says that each is given a small amount of processor time. So we will talk what is that. And wait while other threads are executes. This is also we'll talk. SQL Server uses OS threads to perform its work, right? So SQL Server uses OS threads to perform its work, called as a worker thread. Dedicated thread exists. So these are all about the thread, right? Thread, you understand, is the smallest unit. It takes care of your work. Now, what happens when a thread is created? Okay, let me show you this here. So now I am talking in terms of scheduler, right? So let's say this is your this is your processor. This is another processor. This is another processor. This is another processor. I have 4 processors on the computer. Now, whatever threads that I have here, or the workers or the threads, anything. So it assigned to a task, right? A task will be assigned. Okay. So you have a task created at the SQL Server side, right? So this task will be assigned to a thread or a worker, right? This task can be anything. Let's say, for example, it is your select query, select star from table. So this task has to be executed, and this task is assigned to a thread. So how this will be executed? A thread has to be scheduled on this processor, right? So schedule is nothing but, let's say you have in a company, in an organization, you're working, right? So likewise, you have a different shifts to take care of your work or take care of the load, right? So you have shifts. So what happens? First person comes in and completed his schedule or completed his or her work, and then it he or she will go. The next person will come and perform its work, right? So it is a schedule, right? So we call it as a schedule, right? So one person comes between um so 6 to 9, 6 a.m. to 9 or 6 a.m. to 2 p.m. One person completes its work or shift, and next person comes at 9 o'clock and process its work, right? Or next person comes in and perform the pending work, right? Or a new task, anything it can be, right? This is what the scheduling. The threads also has to be scheduled. The threads also works in the same way. It has to be scheduled on the CPU or the processor that we have, right? So it has an execution unit, and this has to be executed. Where this has to be executed? This has to be executed on the CPU, right? So if I execute, then it will be your execution unit. So this is what we call it as a scheduling, right? The thread will schedule the task on this processor, right? So this is what we call it as a scheduling. In SQL terminology, this processor is mapped to scheduler, right? So this logically in SQL terminology, we call it as a scheduler, right? Each processor is mapped to one scheduler in SQL terminology. Scheduling 1, scheduling 2, scheduling 3, 4, right? So likewise, it is mapped to one relationship, right? So each processor will be mapped to one scheduler, right? So where it executes the queries, right? Suppose if you go here, select start from sys.dmos is a DMV, right? So you have something called schedulers is the DMV, right? So if you execute this, and you'll have, you can consider that hidden and all, like I'll just consider that online schedulers where status equal to visible online, right? So remaining you can ignore. I'll tell. So you have 4 CPUs, right? It is mapped. See, for example, 0, CPU 0. That's what I said, right? Let's say you can consider that this is a 0, this is 1, this is 2, this is 3. The scheduler or processor always starts with 0. It doesn't starts with 1. It always starts with 0. Let's say it is a 0 scheduler. It is first, second, third. Likewise, it is mapped to scheduler 0, scheduler 1, scheduler 2 in SQL terminology, scheduler 3. That is what we see here. right? So if I execute this, right, even if you execute this, you will see, I'll just clear this. Even if you're in your mission, if you just execute this, you will see that whatever schedulers that we have or CPUs that we have, you have the schedulers, 4 schedulers, and you have CPUs 4. 0 0 mapping, 1 to 1 mapping, 2 to 2 mapping, 3 3 are mapping, right? So these are the scheduler and CPU mapping. Now you can see here, each scheduler, you have different tasks, right? So current task count are 7 7 6 8, or different tasks that you have, right? Each scheduler, we have a different task. Now understand, for example, you have a only 4 schedulers. So if you have a 4 CPUs on your computer, and it is a multi, you can consider that multitasking process. Let's say, for example, SQL Server. In SQL Server, it is a multi-thread and uh, multitask process, right? So where you can execute multiple tasks at the same time and multiple threads at the same time. Now, so we have 4 schedulers. How these threads will be executed here on the scheduler? How the threads will be executed on the scheduler? Let's see. We don't have a SQL operating system. What will happen? We don't have. So we don't have a SQL operating system. So now what will happen? In SQL Server, let's say 100 users are connected, right? Hope you are able to correlate or understand. Suppose if anything you feel you are diverting, so let me know. I'll just try to explain that again, right? So these are the basics. Make sure that you are clear, right? So this is what we usually do, right? For example, um, let's say you have a threads. I mean, in general terminology, that you, if you are a DBA, you might see the thread exhaustion, right? So whatever threads that we have, all threads are exhausted. All the threads are, you don't have any more threads to take care of the work. What will happen, right? So you cannot even perform any work, right? Likewise, in non-yielding, the thread is not yielded from the CPU, right? So at least you should understand the terminology so that you can correlate whatever work that we are doing in your day-to-day life, right? So you need to understand how many workers created, like how that works. So these are the basics. If you understand, the way, the better you understood, the better you would be able to um, troubleshoot any of the internal issues or any of the issues with terms of thread scheduling and all, right? If you are anything not clear, feel free to stop and ask me so that I'll try to cover. So I'm just trying to repeat the things because I wanted to make sure that you are able to understand things, right? Now, going back to our question. So but let's say we don't have a SQL operating system. So what will happen? If I consider this is your SQL, this is your process, your SQL server, and you have multiple CPUs. Now, let's say 100 users are connected or 200 users are connected, anything, right? So any in a multi-user system or multi process system, you can have any number of users connected, right? So let's say 200 users are connected and they are executing 200 different tasks. Now these 200 tasks or 200 different tasks will be created, 200 threads will be processed by 200 different threads, parallel threads at the same time. Now, what will happen? So while coming to the CPU, so I have only 4 CPUs, right? So 4 CPUs, how this will be processed, right? So remember, whatever query that we are executing or whatever thread that we are executing, on the CPU at any given point of time, only one thread can execute, right? At any given point of time, suppose if one thread is executed, then remaining thread has to wait for this thread to complete its execution. Let's take this. So how this 200 threads will be distributed? I have 4 CPUs, and how these 200 threads will be distributed. So the distribution is equally distributed in a round robin fashion. So round robin fashion as in first it will execute, it will um, allocate one thread here, next year, next year, next year. So again, allocate another thread here. So likewise, it will be distributed, right? So let's say, likewise, I have 50 threads here, 50 threads here, right? So 50 threads here and 50 threads here. So I have equally distributed the number of threads, 50, 50, 50, and 50. Now, so I have 200 threads distributed across or among all these 4 CPUs. Now, as I mentioned, at any given point of time, only one thread will go ahead and execute on the CPU, right? So it has one thread executed on the CPU. What will happen to the remaining 49 threads, right? So remaining 49 threads has to wait for this thread to come out of the CPU, right? So remaining 49 threads has to wait, right? So now let's say you don't have a SQL operating system. That's what we were talking, right? SQL OS don't have. So SQL Server, now 200 threads are created because we have 200 different uh, tasks. Now all 200 threads will be exposed to the Windows operating system or exposed to this scheduler or the processor, and it will be waiting on the CPU here at the kernel or the Windows, right? So you can consider this is a kernel or the Windows, you can consider that operating system, Windows operating system, right? So this is the SQL layer. And if you don't have a scheduler, SQL operating system, SQL server. And if you don't have a SQL operating system, all 200 threads will be exposed to the scheduler, to the Windows kernel operating system or Windows CPU. And each CPU will have 50 threads and all are in the waiting, right? All threads will be waiting. Now, how long this thread has to be executed? Keep executing. So what if this thread is keep executing for hours together? It cannot, right? So if it is keep executing for hours together, remaining 49 threads has to wait. It is an infinite loop. It has to be waited because it doesn't have any time slice, right? Suppose if it doesn't have any uh, time limit, it is keep executing. So for that reason, what we have at the Windows level, the operating system level, we have something called, so we have something called quantum. Quantum. One sec. So at the Windows level, we have something called quantum is defined. So it's a defined time slice. How long? Oh, okay. So how long the thread has to be executed? 1 second. Just give me a minute. Okay. So let's see what we were talking. Let's say you don't have a SQL operating system. What will happen? All the threads will be exposed. All the threads will be exposed to the processor or the CPU. And if all threads are exposed, let's say 50 threads are exposed to the operating system or the Windows CPU, and you have all these are in the queue, right? So at any point of time, only one thread will execute on the CPU. Only one thread would execute on the CPU, right? Let's say this thread is executing. It cannot execute in an infinite time, right? It cannot execute in an infinite loop or a time, right? It has to be executed, one thread executed um, at any particular point of any particular given point of time. Right. Um, okay. So it cannot execute in a infinite time, right? It needs to have some defined time. So how long the thread has to be executed. This is called quantum. So quantum will be defined at the Windows level or the kernel level, how long the thread has to be executed on the CPU, right? This quantum value is 4 milliseconds.
Is that what is referred to as the preemptive scheduling?
Sorry, what is that? Your voice is echoing.
No, I was asking if that is related to preemptive scheduling.
Correct. That is next we are going to talk. This is what we call it as a preemptive, right? Preemptive. We'll talk that, right? So I don't want to use those words because those are all new. And yeah, that is you're correct. That is what we call it as a preemptive, right? So here, this 4 millisecond is the quantum, right? So that 4 milliseconds is as soon as this 4 milliseconds is completed, so 4 millisecond is completed, it will come out of the CPU. And this, remember, this 4 millisecond are quantum at the kernel level, the OS level. It is nothing to do with the SQL we will talk about. And if you don't have a SQL operating system, and let's say, okay, just a moment. Just give me a minute. I'll pause this for now. I may have to jump in another call, so I'll just give you a high level and then we'll come back again. Yeah, so what we were talking, so we have defined quantum at the Windows level, right? So after 4 milliseconds, the thread which is currently running on the system will go out of the CPU and will allow other thread to execute, right? So other thread to execute as in like out of this 49 in the queue, so it will allow other thread to execute. So next thread will come in, so it will come out of, it will execute on the CPU, come out of the CPU, right? So come out of the CPU. Now, let's say this 50 threads are completed or 50 threads are doing the same thing, like 4 millisecond, 4 millisecond, 4 milliseconds. So now the thread has to be executed again. Let's say, for example, this is your queue. So this queue is, you can consider that at the quantum completed, right? 4 milliseconds. Then what will happen? It will be end of the queue, the thread one. The next thread executes and it will come out of the CPU. It will be in the next, like a first in first out basis. It will be in the queue, right? Now, once all the threads, once 50 are completed, again, the first thread has to join again. Sorry. So the first thread has to execute again. Let's say this is completed around 20% of work. If this is completed 20% of the work, and this should not start from the beginning, right? From the first, from the so from the starting, it should not begin. It should start from the from the place where it left, or where it so where it left from the CPU, right? From 20% it has to be started. right? Where that information will be stored, that will be stored in some so places. We call it as a context. The context of this execution will be stored in some registry, some place, right? We call it as a context will be written, context of the thread. So this context Mm. Okay. So the context has to be written so that whenever the thread is loading again, whenever the thread is started executing again, the context will be loaded, and this context will have the information, right? So how long the thread executed, and from when the query the thread the work has to be started, right? From where the work has to be started. That context has to be loaded. And now assume that you have 50 threads in the CPU, the Windows scheduler, and if it is doing, you will have a very high context switches, high context switches. So what will happen, these context switches, right? So this context switches will have an additional CPU cycle, right? It will keep increasing the CPU on the kernel level or the Windows level, because it is keep executing and keep writing into the so the register, like so it has to write this context into the register point, right? So and loading that context again into the CPU and writing into the context, writing into the register the context and all, it will be an additional CPU cycle, right? For that, to avoid that context switches, there are different disadvantages. We will talk that. And we have something called SQL operating system. SQL operating system. The first reason is to avoid such behavior of the context switches. Second thing, this is one way this will come out of the CPU because of the quantum. Second thing, the Windows operating system is a priority driven operating system, right? So priority driven at the kernel level. So what does it mean by priority driven? So let's say you have, there are different priorities, right? So let's say you have a high priority thread, low priority thread. So if low priority thread is currently executing on the CPU, if this thread is executing on the CPU, there is a high priority thread comes in, right? So some system thread or some high priority thread comes in, whatever the low priority thread kicked out of the CPU, and it will allow high priority thread to execute. That is what we call it as a preemptive. Preemptive is nothing but the thread will be preemptively come out of the CPU. That, so the preemptive is nothing but, so before even completed, the thread will come out of the CPU on its own and allow other thread to come, allow other thread to execute on the CPU, right? So preemptive is nothing but, so before even quantum completes, the thread has to be come out of CPU because some other high priority thread comes in, and high priority thread will have a first priority if it doesn't have a SQL operating system. To overcome this, right? So first thing, to avoid high context switches. I'll tell you how it will avoid high context switches. Second thing, to avoid preemptive, right? So we have something called SQL operating system, right? So we have something called SQL operating system, which we have to handle that, right? So to understand what is this preemptive and non-preemptive, let's just a high level. Windows uses a priority driven, as I said, right? So priority is one thing it will consider, and preemptive scheduling algorithm, right? So priority driven and preemptive scheduling or algorithm. Threads executes within their quantum, right? So that's what I mentioned, 4 milliseconds. As soon as it is 4 milliseconds completed, it will come out of the CPU preemptively. Preemptive is nothing but on its own. So without forcing by someone, so it will come out of CPU within 4 milliseconds, right? Once the quantum expires, that 4 millisecond is completed, threads are scheduled off and must wait for NT. Like NT is nothing but NT system, whatever the Windows operating system or the kernel, right? To schedule them again. When this will be scheduled again, suppose if 50 threads are at the kernel level, CPU level, once all 50 are completed, again, the first thread will get a chance to execute, right? And second thing, right? So there are 3 points that I mentioned. First, 2 points that I mentioned. First, if I take this, first is high priority. So high context switches, preemptive. Third point, for example, if you have 30 threads, so that 50 threads on the CPU exposed, this 50 has to wait for this first thread to complete. And the first thread, again, it has to wait until the 49 threads completed its execution, right? So the wait time, high wait time for the first thread for it at least, right? Once 44 milliseconds completed, it has to wait high wait time, right? So that is one disadvantage using this Windows if you don't have a SQL operating system. Potential for threat to be preempted before quantum expires, right? So there are chances that the threat can be preempted, right? Come out of CPU before even quantum expires. If there is a high priority threat comes in, as I said, right? Priority driven. If there is a priority 0, priority 1, so then the high priority threat comes in, then the thread which is currently executing on the CPU will come out of CPU. The consideration, the reason for we have something called SQL operating system is what we call it as a cooperative user mode scheduling. So we will talk what is that cooperative. In simple terminology, UMS is a thread pool. Sorry. So we will talk about the UMS, how this works in terms of scheduling, right? I'll just pause this and give me 10 minutes. I'll have to I'm currently on call, so I'm just getting one more call, so I will just connect and I'll check and I'll come back. Just okay. Yeah, so we were talking about the preemptive and non-preemptive, right? So preemptive is nothing but the Windows is preemptive mechanism it works, right? So as I said, these are the points, and threads executes within the quantum, or that is 4 milliseconds, right? Once the quantum is expired, the thread will come out of the CPU and it will allow other thread to execute on the CPU. That is what we call it as a preemptive. Also, if there is any high priority threads comes in, so the thread has to come out of CPU because it will allow other high priority thread to execute its work or its task, right? So these are the preemptive mechanism. Now, why we need a Windows operating like if there is a Windows operating system, why we require a SQL OS? right? So the reason we have a SQL OS, so earlier what we were talking about, so we have this and we are exposing all threads, right? All 200 threads we are exposing at this SQL CPU level or the kernel level. So all these threads has to wait and the quantum happens every 4 milliseconds and it is CPU bound, CPU intensive because everything has to do the context switches, right? Every thread has to perform context switches as soon as it is completed 4 milliseconds of its execution, right? So high context switches can lead to high CPU utilization and thread also has to wait for its turn to execute. Now, what we have in SQL operating system, so instead of doing this, what it does in SQL operating system, right? So this is your kernel. I mean, this is your SQL server, and we have 4 CPUs. Now, so we have in SQL server layer, we have something called schedulers, right? Each scheduler is mapped with processor, each processor, right? What does it mean? In SQL layer, this is, let's say you have a SQL operating system. Each scheduler is mapped to one processor, right? So you have 4 CPUs and it will be created 4 logical schedulers, right? So that's what we see here. If I execute and you see 4 CPUs, right? Each CPU is mapped internally with each scheduler. Now, what happens? Let's say I have 200 users, the same logic, the same thing. So we have 200 threads or 200 users are created. So in SQL level, the logical layer, so the threads will be distributed equally, the same way that we distributed at the Windows level. So 50, 50, 50, and 50. So equally distributed at the Windows, I mean SQL level, right? SQL layer, all the threads will be equally distributed, 200 threads. But how this will be exposed to the Windows kernel, right? Kernel or CPU or processor, right? You can consider that this is a processor. And if it is a SQL operating system, so we call it as a UMS, user mode scheduler, right? This scheduling or the number of threads will be taken care by the SQL operating system. Instead of giving this scheduling to the Windows operating system, SQL will schedule the number of threads. For example, let's say you have 50 threads here. So instead of exposing all 50 threads at the kernel level, SQL will schedule the threads on one by one basis, right? So at any given point of time, SQL will expose one single thread to the scheduler, right? SQL will expose one thread to the CPU, right? So CPU level, now we have only one thread, right? We don't have multiple, we don't have all threads exposed to the CPU. So it will be in the CPU, I mean, kernel level, only one thread. Instead of 50 threads, now we will expose only one thread. Remaining 49 threads, we will have it on the SQL layer itself, right? So SQL layer, we have different queues. We will talk about that. And it will be only on the SQL layer. We have all the threads available. So now this thread, so this is a quantum, right? So, so you'll have the quantum of 4 milliseconds of the quantum. Now what will happen? This thread will come out of CPU and if check if any other threads are waiting. Sorry. So if it checks if there is any other threads waiting on the kernel level to schedule. So since we don't have anything, it will keep executing the thread. It will keep executing the thread. So you will not have high context because you will have more threads on the CPU, right? So this quantum, what we are talking is only with respect to the kernel, not with the SQL layer, right? So what I mean, as soon as it is 4 millisecond completed, it will not go out of the SQL operating, go out of this kernel and go back to the SQL. No, it will not. This 4 milliseconds only for applicable within the kernel level, right? If you have only one thread exposed, so it will continue its execution. It will not go out of the CPU, right? So if you don't have any more threads, when this will go out of the CPU and go back to the SQL layer is there are few um, uh, times, I mean, there are few triggering points where it will go out of the CPU and go back to the SQL server. One, if the query executes, execution completed. If the query completes its execution, then the thread will go back to the SQL layer, right? It will go out of CPU and will go back to the SQL layer. Second thing, if thread needs some resource, right? Waiting. So if the thread requires some resource, let's say, for example, it needs some lock, it needs some memory, or it needs some resources, disk, IO operation, right? Any wait type, anything if it requires to be waited, if the thread needs to be waited, then the thread will go out of CPU, right? So then the thread will go out of CPU and go back to the SQL layer, SQL operating system layer. Third, as a yield point, right? What is that yield point? Yielding is nothing but go out of CPU, right? In the Microsoft code, right? So Microsoft code as in not the application code. So in SQL server.exe is written 90% or 95% is written in C++, right? So completely written in C++. And if this code is Microsoft developers, right, who develop this SQL server.exe, they define some yield points. Yield points, right? As soon as your code, your query is touches this yield point, then the thread has to go out of the CPU. It is internal to the Microsoft. We don't know when this will, so meet that yield point or touch this yield point. That is completely internal to the SQL Server.exe. If your code is touch this yield point, because let's say your query is executing, and your query cannot execute X amount of time. It is cannot be completely non-yielding, right? So if that is the case, then there is a SQL bug. If the thread is not yielded, continuously executing on the CPU, and then there could be a SQL bug because it is not yielding from the CPU, right? That is the case, then definitely it's an issue with the Microsoft code itself. For that reason, Microsoft will define multiple yield points. Let's say it is a 100-line code, for example, just a simple example, 100-line code. Each 10 lines, there is a yield point. I mean, this is just a rough, whatever I'm talking for you to understand. It is not that based on number of lines or number of code, right? So it is based on number of logic. What is the logic it executes, right? So let's say every 10 lines, there is a yield point. As soon as it reaches this 10 lines, the thread has to come out of CPU. That is what we call it as yield point. They'll define that point, yield point, and as soon as it touches this yield point, the thread has to go out of CPU. These are the three main reasons the thread will go out of CPU, not because of the quantum slicing, right? This quantum slice is only applicable at the Windows kernel level, not the SQL level. SQL operating system is designed to handle scheduling as SQL is required, right? So SQL is controlling the scheduling, right? So it has the control of when the thread has to be scheduled. right? So the thread is scheduled and it will be running on the server, right? If any of these are met, let's say the query executed is complete, execution is completed, a resource needs to wait for some resources. If the thread is required some resources, it will go out of CPU, or if it meets yield point. Now, when the next thread will be coming, next thread will be scheduled and run on the CPU. Let's say this is your queue, and this is your first thread, second thread, third thread, right? So all threads will be in the queue in a round robin fashion again. First come, first out, right? First thread will spin on the CPU and its complete execution. As soon as this completed execution, it will go out of CPU. Or let's say this will go out of CPU and it will be placed at the end of the scheduler, right? Let's say you have 50. So it will be placed, the thread is go out of CPU. It will be at the end of the scheduler so that it will allow other threads to complete its execution, right? So I'll show more in details like how that works, right? So this will execute, I mean, it will be in the end of the queue. So it will allow other threads to execute, right? So it is a round robin fashion. So once the thread is come out of CPU, it will go at the end of the queue. Now, how this thread will go and how the next thread will execute. This is what we call it as a cooperating scheduler. SQL Server is a cooperating scheduler. What is this cooperating scheduler is thread 1 is executing, and as soon as it identifies the thread has to go out of the CPU, this will give a signal, right? So this thread will give a signal to the scheduler, right? So this thread will give a signal to the SQL operating system in the queue and asking to schedule the next thread. So it will give a signal. The signal will be, I mean, the thread in the queue at the SQL operating system will respond to the signal and it will, okay. It will allow it will give a signal and it will allow other thread to execute on the CPU, right? So that is how, that is the reason we call it as mm, right. So this will allow other thread to execute, right? So that is the reason we call it as SQL operating system is a cooperating scheduler, right? So that is what we mentioned here, right? So if I clear this, UMS is a cooperating user mode scheduler subsystem. Simply put, UMS is a thread pool, right? So that, as I said, right, the same way thread pool, how it works, right? So all the threads will be in the queue and it will allow one thread to execute on the CPU. As soon as the thread is completed, it will go back to the queue, right? As soon as the thread is completed, go back to the queue at the end of the queue, right? So likewise, it will be in the queue, right? So allow SQL Server to smart about when it works, right? We are controlling when should be how this is executed, right? So we are controlling this. SQL Server is controlling this. Allows SQL specific management of CPU time, right? So this is not defined 4 milliseconds of the time slash. Okay. UMS is a logical, not a physical. Yeah, that is what we were talking, right? So it is a logical layer at the Windows, I mean SQL level. It is not a physical layer, right? So we do not change anti-schedulability behavior, right? So we don't change this Windows kernel level scheduling behavior. So this is just a SQL level. We are adding another layer called UMS, SQL OS, to manage our scheduling threads, right? So we are not giving, so that scheduling behavior or scheduling mechanism to the Windows operating system. Instead of, we are managing, the SQL is managing, right? So this is what it is, right? SQL server has its own thread scheduling called non-preemptive scheduling, and SQL layer. So earlier we were talking about the preemptive driven, right? Whenever a high priority thread comes in, the thread will kick out of CPU, and it will allow other thread, high priority thread, to execute, right? So the high priority thread, if there is a high priority thread comes in, then the thread will go out of CPU. In SQL Server, there is no priority driven, right? Whatever threads we have here, 50 threads, all are the same priority. For example, if you go and check the SQL error log, sp underscore read error log and text format, and if you see here, right? So if you see here, control home, and you will see as priority base, right? SQL Server is starting at normal priority, right? So whatever threads which are coming in, all are with the same priority 7, right? So there is some priority levels, right? It is not that first, second, third, like that, right? It will be in uh different stages, right? 1 to 7, like 7 to 20, like, so you'll have those priority level. So SQL Server threads, whatever executing, all are with the normal priority, that is equal to 7, priority 7, right? So that's why we don't have a different priorities to execute our workload, right? So all threads are with the same priority basis. Is more efficient than Windows scheduling. So it is more efficient than Windows scheduling because Windows, we are exposing all threads, that is leading to a different performance issues, right? Performed by OS layer of the storage engine. So this is at the SQL layer, right? So this is what it is. Each processor cores or has a scheduler, right? So that's what we were talking. Each core is logically mapping with one scheduler or processor scheduler, right? A scheduler is responsible for managing the execution of work by threads, right? So this is what we were talking. Each scheduler is managing the thread execution. So this is for both user threads and internal operations as well, right? So you can see that in the sys.dm underscore OS scheduler. That's what I was showing here, right? You see that this is the scheduler address, whatever it is in scheduler, and it is mapped to one and visible online. So either it is online or not, right? You see here, I is idle because we don't have any threads executing on these schedulers, right? You have this individual. I mean, so if it is 0, it is not idle. Currently, something is happening. And you see here the current task count, right? It is equally distributed on an average, right? So 7768, the threads are equally distributed. The tasks are equally distributed in this scheduler, right? So it has 7, next one 7, 6, 8. Likewise, current worker count. This is also on an average equally distributed, right? On this 7 tasks, maybe you have 12 workers are created, right? Whatever. So currently this is also distributed equally, right? So this is the active worker count. How many workers are currently active on an individual schedulers. right? So this is the active worker count that we have, right? So this is what it is. Load factor is 6668, right? So load factor is nothing but how the data is distributed, how the threads are distributed across all the scheduler, right? So this is just a load factor is like 6 threads, 6 threads. This is on an average, it is scheduling, right? Quantum length, see here, this is the quantum length. This is in microseconds, I think, right? So this is, you can consider that as 4 milliseconds, right? So this is defining at the Windows level. This is nothing to do with the SQL layer. Like that is the reason every time that you execute, even if it is running for an hour, it is keep executing, right? So because it it has, I mean, it is not nothing related that it has to be a quantum of 4 milliseconds or something. Yep, right. This is what here, right? So if I show you here, right, this is the actual how this is scheduling, right? So you have, this is called CPU 1 and CPU 2 and CPU 3 and CPU, like this is at the kernel level. And you have the scheduler 1, scheduler 2, scheduler 3, and you have a one-to-one mapping between CPU and scheduler, right? And each scheduler, we have different queues, right? So if I go here, I'll come to this. Before that, their reason for having this UMS goal, right? We were talking earlier, right? So UMS goal, control which thread should run from the SQL server, right? So we are controlling the SQL operating system. We are controlling, or SQL server is controlling when should we run our load at the Windows, I mean CPU level, right? We try to run one thread per CPU. It is always, right? Either we have a SQL operating system, or if you don't have a SQL operating system, at any given point of time, only one thread will go and spin on the CPU or execute on the CPU, right? So we try to run one thread per CPU, but there are exceptions. Let's say, for example, parallelism or anything that we will talk later. Priority is irrelevant. That is what we talked. There is no priority driven, right? So whatever threads that we have, all are with the same priority. So priority is irrelevant. Not complete scheduling, just some construct to make a better decision when we allow OS to schedule our threads, right? So um, we are allow so our SQL server to schedule, and the OS level is what, like we have how the threads has to be handled, right? So the OS will take care of the thread handling, but we are at the SQL level. We are deciding when to when the thread has to go and execute on the CPU. See, context switches. That's what we were talking, right? Avoid causing a thread to switch into a kernel mode whenever possible, right? So we are avoiding that. Support asynchronous IO. We will talk that like later. Asynchronous IO is nothing but, for example, you posted one IO request. The thread doesn't require to wait for that IO to be completed, right? So asynchronously it happens, right? So the same way that we have always on asynchronous, right? Whenever there is a, so query executed, primary will not wait for the confirmation from the secondary. The same thing asynchronous IO is, when the thread is posted in IO request, IO operation, it will not wait for the IO to complete, right? So that we will talk more in detail in IO when we were talking about the IO, right? So that is the design goal for UMS. Let's understand few terminologies that we already covered. Quantum, right? The time slice a thread is given to run by the Windows scheduler, right? So as I said, Windows scheduler, it is at the Windows layer. We are letting the thread to run in a specific time. Windows creates an illusion that all threads run concurrently by partitioning the time each thread is allowed to run. This is same thing. The quantum is 4 milliseconds. It is thinking that every 4 milliseconds that thread has to execute and go out of the CPU. Go out of the CPU within the kernel layer. It is not related to SQL OS. Context switches, saving information for old thread, loading information for new thread, right? So the thread is come out of CPU. It has to save that information in the some registry point, right? While the thread is loading again, it no need to start again from the beginning. It will be loading the same context back or same stage where it is come out of the thread, right? Now, so there are different states of the thread. For example, if you execute query, let's say select star from sys dot sys processes. Like what is the table, what is the catalog that we usually execute, right? So DMV that we usually executes. So if you execute this, whatever state that we see here, right? So state is not equal to, let's say, background. I don't want any background threads. Okay. So let's say the state is, this is what we call it as a thread states, right? So what is the thread states? So you can consider that is a thread and it is different states, right? What are the states that we have? Sleeping. And here if I take runnable, if you can see, like, so different states, right? So what are the states? Sleeping, running, runnable, suspended.
Spend.
Hmm. So anyone wanted to give a try? I want you to, I know like we are keep talking theoretical, like anyone wanted to try what these are? Like when you see these weights, when we see the sleeping, when we see running, we all know like when is runnable, when is suspended. Anyone wanted to give a try when that thread will be in sleeping state?
When the thread is in sleeping state, that means it's idle, so it's not working at that time.
Okay, the thread is idle. Okay, not
Yeah, and when it's in running state, it means it has um, acquired resources and it gets into the running state.
currently it is running. Okay.
Yeah. And when it's runnable, that means at this point it's might have given up its resources
Hmm.
because the running state, if let's say at the running state, it requires more resource to continue running. Probably it's running for too long.
Hmm.
It gives up its resource
Hmm.
and goes into the runnable state. That
Hmm.
means it's still waiting for resource to start running again.
So
So,
resource as in like what do you mean by resource?
for example, it could be waiting for CPU.
Hmm.
It could, yeah.
Okay.
Runnable state means is waiting for more for
Hmm.
CPU to start running.
Hmm.
And suspended state um,
Hmm.
suspended state, that is when it's not, but I think at suspended state it's uh, I'll check that thing.
Yeah, sure, no problem. Yeah. You're correct. Like whatever you mentioned, that is correct, right? It is simple, right? So then simple than like runnable, that what you talked. Anyone wanted to talk about suspended or any objections in what we have here, right? Anyone wanted to say about suspended? What is that?
I can try.
Yeah, sure.
When it's suspended, is it temporarily paused or halted?
Temporary paused. What do you
I
mean
says
in terms of SQL? Huh.
in SQL is maybe suspended. Maybe it was running
Hmm.
and as a thread has been temporarily paused. Is some suspended? Probably there's been blocked for a long time, or suspended,
Hmm.
or
So, like maybe waiting for the resources, we can say.
Yes, that is what it is. And thanks. That is you mentioned, right? So blocked is basically the underlying wait, right? So it is waiting for some resources, right? So if the thread is waiting for resources, then it is what the status will be suspended, right? It is not currently executing, right? Um, and tell me one thing. So let's say, for example, if it is waiting for uh, some resources, let's say, for example, it is waiting for lock or blocking. Or waiting for something, right? Do you think it takes additional CPU cycles? Is CPU, it uses the CPU or not if it is waiting?
At what state? At the suspended state?
Correct. If it is waiting, it is suspended. Yes.
Yes. So it at this point, I think it already has its CPU, but it's locked. So once it's able to acquire the lock,
Mm.
then it should be able to execute. But if it stays at this level for too long, then it can where it doesn't. But anyway, at this level where it's waiting for lock,
Mm.
it's still using its CPU time. So has not yet released the argument. Understand?
No, no, no. So you mentioned two things. One is it will not. Whether it,
No, 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 what I'm
it,
saying, sorry,
uh,
okay, let me put it straight. What I'm
okay.
saying is where it's waiting for lock,
Okay.
where when at this point it's waiting to acquire lock.
Hmm.
So it still has its CPU time.
Hmm.
Yes, it still has its CPU time and it's waiting to acquire lock.
Correct.
So
So let's say, for example, so 10 minutes it is waiting to acquire a lock, right? It is waiting. So I'm not telling that it is currently executing. It is waiting for the resource or waiting for something. So now you see that CPU time is the same amount, right? So 10 minutes, whatever, or it might utilize less CPU cycle because this is waiting for something. So if you recall what we talk about, here, this one, what is this? So when the thread will go out of the CPU, right? If the thread is go out of the CPU, it is not running on the CPU. If it is not running on the CPU, it will not take any additional CPU cycles. When this will go out of CPU, one of these, right? If it is execution is completed. If the execution is completed, it doesn't require to take additional CPU cycles, right? It will go out of CPU. If the resource is waiting, right? So that is what we called as suspended. If the thread is waiting for some resources, right? So this will not take any additional CPU cycles because it will not be on the CPU. It will come out of the CPU. So if the thread in a high level, in a general terminology, if the thread is come out of the CPU, it is not utilizing any of the CPU,
yeah.
right? That is the so that is how that works, right? So the same thing, the thread states running is This is what you already mentioned, right? So just a high level, the thread is currently executing on the processor, right? Where we execute on the processor. Suspended. The thread is currently on the waiter list. List we will talk about, waiting for some resources. Runnable, right? Okay, I'll just give you a high level. We were talking about this. Where is that? So I'll just give you this. Let's say this is, I said, you can consider the SQL OS layer is in the queue because we have these 50 threads in the SQL OS level. Okay, so you have 50 threads. Now, let's say this is your CPU processor, right? So in SQL scheduling, let's say this is your thread 1, 2, 3. Let's say you have multiple threads on this. Now, what will happen? First thread will come and execute here. So currently thread 1 is executing. The thread 1 has to go out of the CPU, go back to the SQL OS. When it will go back, and if it is waiting for some resources, execution completed, or thread yield point, if it meets the yield point, whatever the reasons, right? It will go out of CPU. And if it go out of the CPU, I'm talking high level, so I'll tell different things. It will be there. This thread will go back to the end of the queue here. It will go back to the end of the queue because it will not be here. It will go back to the end of the queue. Until these 5 threads are completed, this chance will not come, right? So this thread 1 will have to wait for this. What it is waiting for? This thread is waiting for CPU to be available, right? The thread that is there here has to wait for the CPU to be available. This thread has to wait for the CPU to be available. Until this is available, the status of this thread is called runnable, right? So the thread which is there in the queue and ready to, not only this, all these threads except the first thread, because the first thread is currently executing on the CPU. All threads are ready. These are all ready. So when this will be executed? As soon as the CPU is available, right? All these threads status is marking as or set as runnable. So runnable is, it is waiting for CPU to be available. As soon as the CPU is available, it will go ahead and execute on the CPU, right? So this is what runnable means, right? So we will talk that, but just a high level, what is that runnable is. The thread is currently on the runnable queue. There are different queues I mentioned. So this is one of the queue waiting to execute on the processor. So it is waiting to execute on the CPU, right? It's a, there are different queues in the processor, right? Each processor will have a different queue. Let's say this is your SQL scheduler or processor. You have a different queues. What are the queues that we have? It is the runnable queue, and you can consider that as a waiter queue, and you can consider this as some timer queue. Let's say timer as in um, frequent execution, right? Let's say checkpoint and lazy writer. I mean checkpoint, some threads. Okay. Fine. So timer queue as in like every frequency the thread has to execute, right? So what are the threads which executes in frequency in a specific time slice? One, checkpoint. some different internal threads, right? So every frequency of executes. What we all know and aware, checkpoint. Checkpoint executes every 1 minute. That is in a timer basis, right? So that is what it is, timer. One of the example, right? So that executes. And what other queues that we have? A worker queue, whatever. Like worker queue is nothing but whatever the worker pools that we have, right? So available workers, like you can consider that as a another thread worker pool or thread pool. You can consider that. And the next one is your IO list. Now IO. So there is a reason we have different queues here. Now let's say this is your CPU and thread executing on the CPU. Thread executes, and this thread is posted some IO operation, right? So then it is waiting for an IO to be completed. Let's say what we call some read or write, whatever it is, an IO operation. Let's say backup or anything it matters, right? Some IO operation it posted. Then what will happen? This thread will come out of the CPU and it will be in the IO list. So that is what we call it as asynchronous IO. So whatever the thread which is posted in IO, the thread is not need to wait for this IO to be completed. So as soon as it is posted, the thread will go back to the IO list and waiting for IO to become, I mean, it will not wait for IO. So IO will be monitored by a different thread and it will be in the IO. As soon as the IO is completed, that is the request is completed, then the thread will start executing. But I will tell you, that is one thing. Or the thread is waiting for some resources. Let's say it requests some lock, or it requests some page, or it needs some memory, right? As I mentioned, if it needs some resource, it will not keep waiting for the CPU, because until it gets the resource, some other thread can execute on the CPU, right? So it will allow. For that reason, if it is waiting for any of the resources, not only limited to this, it can be anything waiting for some resources, then the thread will go back to the waiter queue, right? So the thread will go back to the waiter queue and the timer thread will be in the, let's say, some thread, timer thread, let's say checkpoint thread, or you can consider that lazy writer, or you can consider that schedule monitor. So these are all executes in different time slice in a time interval, whatever time slice automatically executes background threads. And those will be here in the waiter queue. So runnable queue is the threads are ready to run on the CPU. So ready to run on the CPU, right? As soon as it sends this thread to one of these queues, worker queue, worker pool is nothing but if the thread is executed, completes its execution, right? If the thread is completed its execution and it doesn't have anything to work on, it doesn't have anything to take action, it will go back to the worker pool. So a new task is coming in and it will take that thread from the available worker pool and the thread will be placed into the runnable queue, end of the runnable queue. That's what I mentioned, right? Runnable queue, all threads, whatever we execute, it will be going through the runnable queue. The threads will be going through the runnable queue, right? So these will be in the runnable queue. Now, let's say the waiter queue, what we were talking. Let's say it is waiting for some lock, some resource. What will happen? As soon as it gets the lock, what it is waiting for, it got the lock. After 2 minutes of wait, it got the lock. Now what will happen? Immediately it will execute? No. So this cannot directly execute. Other than runnable queue, none of the queues will execute the threads, right? So only it will go through the runnable queue. So as soon as it receives or it acquires a lock, the thread will go back to the runnable queue. Go back to the end of the runnable queue, and it will wait for the CPU to be available, right? So likewise, timer, the thread has to be executed. It will go back to the runnable queue, and from the runnable queue, that thread has to be executed. Let's see, likewise, IO operation. So the IO posted is completed. Then it will go back to the runnable queue and execute from the runnable queue. So likewise, worker, a new task created and a thread from the worker pool assigned. Then it will go back to the runnable queue and start executing the query, right? So whatever threads we are executing all through the runnable queue, right? If you see here, the list of the process that are ready to run, right? It is ready to run. Waiter list, a list of processes that is waiting for some resources to become available. For example, lock or memory or anything, right? It requires some memory resources. And worker queue, a list of processes that are queued to given a scheduler, right? So you have a task created that has to be assigned to a worker. So this is taken from the worker pool. Timer, a list of timed process that are signaled to run on a regular interval. Let's say checkpoint, lock monitor. So all these are, uh, so in an interval it executes. IO request, a list of IO progress and pending IO request that needs to be completed, right? That is a asynchronous IO, or the IO operation is performed, right? So that is, for example, sorry, checkpoint. Even checkpoint has to perform some IO because it has to flush the data pages to the disk. That is an IO operation. That also through the IO request. That is an asynchronous IO. That happens through the IO queue that we have. Right? So that is what it is. So this is just a high level that we talked, right? The waiter list is a unordered list of threads that are suspended, right? So that's what I was talking. If it is suspended, it is considered as a waiting for some resources, right? Any thread can be notified at any time that the resource it is waiting is available. Suppose if the thread is waiting and it receives it acquires the resource, then it will go back to the runnable queue. Okay. There is no time limit, right? It can wait for any X amount of time, right? Although execution timeout or lock timeouts may take effect. Like for example, let's say you have lock timeout or execution timeout or query timeout. If you define that, it will wait for certain amount of time. Let's say you define this lock timeout or query timeout is 10 seconds. If it is waiting for more than 10 seconds, it will be timing out, right? So that is the some exceptions that we can do that. So there is no limit or there is no restrictions that you'll have to have this only 10 threads or 20 threads in the waiter list. No. This is one of the DMVs, right? So where we can see that how many tasks are waiting waiting in the scheduler, right? So if we execute, select star from sys.dm underscore os underscore waiting task. Right? There are two DMVs, right? For example, select star from, yes, any questions? There are two DMVs, wait stats and waiting tasks. We will talk more in detail about these two and the when we're talking about the wait stats and wait this one. Let's say these two are DMVs. This one will give the historical data, like since the SQL is restarted, this will tell like what are the current waiting tasks that we have, right? So we will talk in detail, but this will give the current waiting task. This will be giving the current waiting task, and this will give the historical waits since the SQL is restarted, right? So that we will talk in detail, right? So it shows this. Shows which thread are currently waiting and what are they waiting for, right? So it's a runnable queue. If it is a runnable queue, it's a first in first outcome basis, right? So as I said, runnable queue, only the thing the threads will go and execute on the CPU. Sys.dm OS schedulers DMV shows the size of the runnable queue in runnable task count, right? For example, if I go executed here, I'll clear this. Runnable task count, right? How many tasks are in the runnable queue? I don't have anything, right? So I don't have anything. So that's why it says that runnable task count is 0. Nothing is in the queue. It is simple idle system that I don't have anything here. Is strict first in first out basis, right? Whatever the resource governor and all, it's a different thing. Sys.dm underscore voice scheduler DMV shows the size of the runnable queue in the runnable task count, right? So what we have here, this is the pictorial representation. For example, let's say you have different schedulers. That's what I was talking. Runnable, you have the runnable, IO, timer, worker pool, and waiter list. So you have a different schedule. Let's say, for example, a thread is currently executing here. You can consider this. Thread is currently, this is the CPU. Currently executing on the CPU, right? Now the thread has to be come out of CPU. I mean, the thread is completed its execution, whatever it is. If I click next, see, this is going back to the runnable queue, and whatever the first thread in the runnable queue is going and executing this, right? Just to understand, whatever thread which is currently in the runnable queue, it will go back to the end of the runnable queue. Sorry, whatever the threads currently executing on the CPU, it will come out of the CPU for whatever reason. It will go back to the runnable queue, end of the runnable queue, and the first thread in the runnable queue will go ahead and execute it, right? So that is what it is. Go back and worker, next, it is executing. Now, let's assume that you have different queues here, right? Next one, if any of the queue is wanted to execute the thread in this queue, it will not directly spin on the CPU. It will not directly execute on the CPU. Instead, it will go back to the runnable queue, end of the runnable queue. And from there, it will wait for CPU to be available. Next, see IO list, the first thread in the IO list. And it will go back to the end of the runnable queue and waiting for the thread to execute. See, likewise, if it is a timer also, it will be done the same thing, right? So it is waiting for runnable queue and waiting for run thread to be available, right? So the same thing, waiter list, right? All are in the same list. So the priority, if these three are there, the priority is, first priority is given to the IO because the IO is important and it should be on priority. I mean, there is no priority, but out of these, which thread has to have this priority is this, right? IO list is first priority, then timer, then the waiter, right? So, but again, the priority is not to run on the CPU. Priority is to be in the runnable queue, right? Timer is next and waiter is the next, right? So this is how the threads will go ahead and execute on the CPU, right? So this is the different queues that we have, right? So in a high level, you can consider this, right? So what we all discussed, pending, right? Pending is nothing but you can consider that thread is not available. Then the thread has to be, a task has to be waited. It doesn't have a thread to take care of action, right? This is what it is. The pending is. I have no thread and no CPU to be available to execute. Runnable, I have a thread, but not CPU. It is basically in the runnable queue. This is the CPU. This is the CPU. Whatever. So you can consider that. So this is the CPU which is currently executing. That's why I have a thread and I have a CPU. And the status you see, it is currently running. Currently running. Because the thread is currently running. If I'm not doing anything, right? So the thread is come out of CPU and not doing anything, then this is what it is sleeping, right? So the thread is currently sleeping state, right? So the thread is currently sleeping state if it is not doing anything. Suspended is something that the thread is currently waiting for some resources. I am waiting for an IO to be available. This is just a high level, but waiting for some resources. It can be anything, right? So it is waiting for some resource to be available, right? Suspended is nothing but waiting for some resource to be available. So this is the states that you might see when executing any queries: runnable, suspended sleeping, running. So these are the main. So if the thread is not even available, maybe thread exhaustion or something, that you will see the thread is waiting for thread to be available, right? So that is what it is. The overall, like how the scheduling works and how the scheduling handle the threads. This is just a high level. How thread will be handled. Let's say you are getting an incoming request. Either it can be a SQL select, or it can be anything. Let's say it checks whether the idle worker is available, right? So if there is a worker is available, then assign the worker, then it will be in the runnable queue. If the worker is not available, right? So it will check whether either the worker limit exhausted, right? So they, let's say for example, 4 CPUs, there is a certain limit, 512 threads, right? If the threads are exhausted, the limit is reached, then you are not able to execute anything, right? Worker request is in queue until the worker is available. If the worker limit is not reached, but you don't have an idle worker, but worker limit is not reached, right? Then it will create a new worker and assign that worker to the task, and it will be processed its execution. Again, all are linked to the runnable queue. Whatever threads executing, it will be going through the runnable queue of our execution, right? So this is your this is what internal, how the threads will be handled and how these requests will be processed, right? So any questions on this, or anything clear, or anyone wants anything to clarify? I'll stop here. I mean, anything, if you want to understand, or anything is cleared or not cleared, or if you want me to repeat anything, let me know. I am okay to do that, but just to make sure that you understand the concept, right? So any questions? Any questions? Are all clear? So we will talk about the weights and all, like, so we'll see that, like, you might see runnable queue. Runnable, so the thread is currently waiting for waiting for CPU to be available. So you might see that high runnable queue, right? So what weight types that you will get, right? So that is runnable queue. You might see something called SYS scheduler yield. SQL SYS is nothing but SQL operating system scheduler yield. It is waiting for whatever thread which is currently scheduling. It is waiting for this thread to be yielded so that your next thread in the runnable queue has to go and execute. Right. That is what we call it as a scheduling SYS scheduler yield. Right. When to consider that is an issue, right? So we will talk that in our next class, right? So any questions on this so far? At least the concept is clear or not?
Yeah, the concept is
Cool. Other others like you, is it clear or is it too much?
Yeah, it's clear. Yeah, it's clear.
Cool. Um, Chandu, Aditya, and I don't know who's
Yeah,
requested.
it's clear.
It's my first day. It is a very deep explanation. I need to recall it again.
Sure,
From the
definitely.
first videos.
Yeah. So definitely you go through the recording. Suppose if
Yes.
you need any clarification, I'm open to discuss this complete thing in our next class. Like usually we were thinking to have 2 days in in a week. It was yesterday and today. I see like yesterday there were no, I mean only a few joined. So yesterday we skipped and today we have taken. The next class will be next week. Tomorrow I cannot. I have some other works and I'll have to go to the office. Next week we'll connect and it will be 2 days, right? So try to join on time under 5 or 10 minutes delay. That's fine. But yeah, try to join so that we will continue our sessions. And next session, go through the recording. I will ask Shanmukh to share the recordings and go through. And if any doubts or any clarification or anything, if I missed anything, so I will cover. Or if you need any clarification on that, I am open to talk about. Right. So definitely
Thank
it
you.
is some internals and people who might heard like, so little here and there, they might understood the concept. But if it is completely new or anything going internal or inside internal, like suppose if you overlook or if anything you missed, so it might be kind of so completely slipped out of your mind, right? So for that I am open to cover in next session. If you have any questions or any doubts, just let me know before I start the next session so that I'll cover this topic. Okay, so if any doubts or any questions.
Okay, sure.
I have a quick question, please.
Yes, sir.
Are we going to cover some details about the different weight types?
Yes, not all, but because we have so many, right? So not all, but um at least
Yeah,
major weight types I'll definitely cover.
yeah, I'm interested in the
Hmm.
network. Async I
What is
weight
that?
type. Async,
Async.
yeah.
Okay. IO, okay. Network async or IO,
Well,
IO
yeah,
async. Uh-huh.
exactly. I'm trying to put
Okay, fine,
the
fine. I got your point, right? So async, yeah. So we'll cover that, and anything that you feel that like it needs to be covered, so that so I'll make sure that it is covered, right? I don't want anything. You just tell me like I'll give you the high level, like whatever I'll cover. So can you guys tell me like one or two weight types that you feel that it is important based on your day-to-day work that you see, right? So resource MA for query compile, CX packet, or parallelism, and as well as scheduler yield, thread pool. These are all weight types I will majorly cover, right? Anything that you feel like async network IO, async disk, async IO, async IO, I'll cover all these. Anything that you feel that needs to be added to the list, the weight type, either you tell me now, that's okay. Like even if you tell, so in our next session, that should be fine. So that I will have those in the list. Okay. Cool. I'll cover that. Like, so most probably uh I'll cover in next 1 or 2 sessions, I'll cover this weights and weight types that we will discuss. Okay. So I will stop here. If you have any questions, open to discuss. If not, we are good for today and this week. And we'll connect next week and we'll discuss on that. Yes. Okay. Thank you. I'll stop recording.